So far we have almost exclusively studied resistive circuits, and by definition a resistive circuit contains only resistive components. And what a resistive component was is that the current voltage relationship is described by an algebraic equation. Okay, so its terminal equation is in the form of an algebraic equation. Henceforth, we will extend our understanding toward dynamic circuits. That means we have to understand first dynamic components. Okay, and to this end, we will extensively study two very important dynamic components, namely LTI capacitor and LTI inductor, where the terminal equation is not in algebraic form, and by terminal equation I mean the relationship between current and voltage. Okay. Instead, the terminal equation is in differential equation form, or sometimes integral equation form. Okay. Or for our analysis, we will find to work with certain functions quite helpful. Therefore, before even we start reviewing our knowledge about LTI capacitor, we now introduce some so-called elementary functions, okay? Because we will make use of them in our analysis. Okay, there are three elementary functions that we will find useful in our analysis. And they are these. Okay. Okay. One of them is so-called unit step function. Okay. And it has the following shape, which makes it clear why it's called a step function. Okay, so it's zero for all negative values of t. It's 1 constant for all positive values of t. And at exactly t equals 0, the value that it takes, well, we don't simply care. You can take it to be 0, you can take it to be 1. Okay, you can take it to be 1/2, or you can take it to be all the values between 0 and 1. Okay? So it's not really that important. And we denote it by the letter u. So that's our first elementary function. And then we have the second elementary function. Okay, it's called unit ramp. Unit ramp function, and it's noted by usually r, okay, r of t, and how it's defined is, again, it's 0 for all negative values of t, and t usually denotes time. And starting from 0 to the future, okay, it climbs with constant slope of 1. Okay, the slope is this argument ramp function. Quite easy, in fact a little bit boring functions, okay? And now the third member of our set is a little bit more interesting and perhaps a little bit more difficult to understand, okay? If nothing else, it's much harder to draw. It has following notation, okay, Greek letter delta. It's called unit impulse function. Unit impulse function. Sometimes it's called the delta function, and sometimes it's called by the name of its inventor, okay, Dirac's function. Okay, delta function, and it's really not possible to draw it in the sense that we are able to draw u of t and r of t, but it has the following symbolic representation. Okay. We draw an arrow, and somewhere close to the arrow hat we put in parentheses number 1. Okay, so that's okay. That number will become clear later on. And of course, this picture is not really a proper definition of delta t, so we have to say more about that impulse function. But one thing that's clear from this picture is that it's 0 for all negative values of t, and it's 0 also for all positive values of t, but it does something remarkable just at or around the origin. And what it does is as follows. Okay, so we have to now get a more understanding on delta function. Okay, so what's really impulse function? Okay, one way to visualize it is through a limiting process. Okay, now consider the following so-called pulse function, okay, which is 0 for all negative values of t, and for a small interval around the origin, it's constant at some non-zero value. Okay, and then for later times, it's again 0. Okay, so here 0 for negative times, 0 for times later than some, well, usually tiny positive time, okay? And then between 0 and delta, it's positive and non-zero. Now, it's the value that it takes is such that this area here is always constant, and that constant is this number that appears in the parentheses 1. And this pulse can be written in terms of the step function that we just introduced. Okay? This is no other than ut minus delta. This is, in a sense, delayed step. And then you multiply everything with 1 over delta, or you divide thing by the delta. Okay. And now this is about the defined function and how we move from this construction to the impulse function is through a limiting process. Okay. Now one way to define, I say one way because there are many other ways, equivalent ways to reach this function through a limiting process. Is as follows. Delta function can be defined as the limit as delta goes to 0 from right, ut minus delta over delta. Okay. Now as you squeeze this interval further and further, as delta becomes smaller and smaller, since the area has to be constant, its height should raise higher and higher, so that the product delta times 1 of delta is always 1. Therefore, delta t is 0 for all non-zero values of its argument. Okay? And at t equals 0, it has some peculiar singularity. Okay? And to understand what that singularity does, the best way is to pass this function through an integral. Okay? So singularity, what we mean by singularity? Singularity is such that when you integrate it, through any interval that contains in its interior the point 0, the result is 1. For all alpha beta positive. Okay. Now our set is complete. We introduced step function, ramp function, and delta function, and it's not difficult to observe that those three functions are related to one another through integration. Okay. So these are easy observations to make. So from minus infinity to t. Okay. If you integrate the impulse function, what you obtain is step. Okay, unit step. And if you integrate step, what you obtain is ramp, unit ramp function. This is r of t. Okay. And by convention, henceforth we're going to take impulse in certain parts of our analysis. We will let impulse to be the derivative of step, even though the step function is not differentiable in the proper sense of the word. Okay, so d over dt ut, and we will let step to be the derivative of ramp function. d over dt rt. Okay. Now, those are our functions, step and ramp. They're quite straightforward to understand, to visualize. As for the impulse, we have to understand it a little bit in an indirect, more indirect fashion, and it's best one way to understand it is through this limiting process. Another way to understand it is that it's what it does under integration. Okay, because everything is finite when you consider the integral definition, everything is well behaved. Now let's see a couple of examples in order to gain some familiarity with this new set of elementary functions. Okay. Now this is our first example. Sketch function f of t, which is defined by a step function as follows. 2u, and the argument of the step is minus t minus 1. Okay. So some of you see what f of t should be directly, but since it's our first example, let's adopt a little bit more formal way to solve it. So therefore, let us introduce new argument s, which is minus t minus 1. Okay, so that's the argument that appears inside parentheses here. And with that new variable, let's write down what 2u of s is, and 2u of s is quite straightforward. What it is, all you have to do is you just multiply everything by 2 for a unit step. So this is 2 times unit step, which is 2 for s positive and 0 elsewhere, s negative. Okay. And now translate s larger than 0 and s smaller than 0 in terms of into conditions in terms of t. Okay, so s positive means minus t minus 1 positive, and that means t t is smaller than minus 1 and s negative, then we mean the other direction, t greater than minus 1. Okay, so what f of t therefore is, it's 2 when t is less than minus 1 and 0 elsewhere. Okay, hence t can be described by this piecewise fashion: 2 for t less than minus 1 and 0 for t larger than minus 1. Okay. And how it looks like is here, t, this is where the things change, okay, minus 1. For t larger than minus 1, f of t is 0. Okay, so it's 0 throughout all those points here. And at t equals minus 1, it moves, it jumps to magnitude 2. Okay, so when t is less than minus 1, its value is 2. Okay. Let's see another example. Again on our elementary functions. This time f of t is given. It has this triangular shape, symmetrically positioned with respect to the origin. Okay, this is 1, this is minus 1, this tip reaches magnitude 2, f of t. Okay, so it's 0 for all values of t less than minus 1. It's 0 also for all values of t that's greater than 1. And between minus 1 and 1, what it does is it raises, okay, it grows with slope 2 between minus 1 and 0, and then it descends with slope 2 or minus 2, or goes down with slope minus 2 for the interval 0 and 1. And what we're asked is to express this waveform, this function, in terms of elementary functions. Okay. Impulse, step, and ramp if need be. Okay, so what we're going to do is we're going to decompose this f of t and try to write it as sum of certain functions, and those functions are written down in terms of impulse, step, or perhaps ramp. Okay, so what we're going to do now is very similar to what we did when we were analyzing one-ports that contain ideal diodes. Okay, it's the same decomposition process. So here is the solution. So this is our function that we want to decompose. Minus 1 t. Okay, now this equals what? Now, let's forget about what it does exactly once it passes point t equals 0. So therefore, let's only concentrate on this part. Until t equals minus 1, it's 0, and starting from minus 1 to the future, what it does is it grows with slope 2. Okay? So the slope is constant. Therefore, whenever the slope is constant, we think immediately of the ramp function. Okay? Now, the unit ramp has slope 1. Okay? So to make it slope 2, all we have to do is multiply that thing by 2. And also, another difference between this function here and the ramp function is that the ramp function starts growing at t equals 0, whereas this guy does that a little bit earlier. Okay? But that's also a minor difficulty. You can always modify the argument accordingly. So therefore, this equals, okay, for a while at least, minus 1, and then equals 2t0. Okay. So at least until t equals 0, this function f of t can be realized by such a waveform, and this waveform is 2r t plus 1. Okay, because the argument is t plus 1, it means that it becomes, the overall argument t plus 1 becomes positive once t passes the border of minus 1 to the right. Therefore, it starts raising at t equals minus 1, and this too guarantees that the slope of climbing is 2. Okay, now this represents this f of t, not for all times, but at least for times for negative times, okay, until t equals 0. And then we have to take care of that part when t becomes larger than 0. And for that, okay, what we need is the following. This is t. So, first of all, whatever this function is, it has to be 0. Okay, until t equals 0, because we have no problem with this representation until t equals 0. This and that is the same. Okay, and then what we want this guy to do is we want this guy to take care of this part, because this part and that part, they don't match. Now here the slope is 2, and here the slope is minus 2, and therefore to make this slope 2 minus 2, what we need is we need a slope of minus 4. Therefore, minus 4. With such a waveform, what's going to happen is it will raise this plus that will give us, everything is same as here until t equals 0, and starting from t equals 0 onwards, it will start going down with slope 2 plus minus 4 minus 2, just as here. Okay? But that slope of minus 2 will continue forever if you don't do any further modification. Okay? But that slope of minus 2 remains, okay, becomes 0 at t equals 1 and remains 0 for future times. Therefore, to this we have to add yet another function so that the sum will give us f of t. By the way, this is the ramp, okay, but it's upside down, therefore we have to put a minus sign before, and its slope is, the magnitude of its slope is 4, therefore it's minus 4 RT. Okay. So far what we have is this plus that, which yields something like this. Okay. Minus 1, 1, this is 2. Now everything is fine until t equals 1, but here the slope is minus 2. From t equals 1 to the future, what we want is we want to remain constant, 0 slope at the value 0. So the last thing that we should add, therefore, should be something that will take care of that unwanted slope of minus 2 starting from t equals 1. Okay. So this is 1, this is 0. So whatever we're going to do, or whatever the function we're going to add, it must be 0 until t equals 1, because we're fine with the representation until t equals 1. And starting from t equals 1, here we have slope of minus 2, and the resultant function has a slope of 0, therefore to balance this slope of minus 2, what we need is slope of plus 2. And here, slope 2. If you add finally that third piece, the sum of those three functions will give us f of t we start with. And this function is rand. Okay? But it starts climbing at t equals 1, therefore it's a delayed ramp. And also its slope is 2, therefore it's not unit ramp, but 2 times it. Okay. Therefore, f of t can be written as sum of 3 ramp functions. 2r t plus 1 minus 4r t plus 2r t minus 1. Okay. Now let's see another example. This time f of t is given as follows. So it's 0 for negative values of t, it's 0 for t larger than 3. Between 0 and 1, it climbs with constant slope of 1. Between 1 and 2, it's constant at 1. And between 2 and 3, it's constant at minus 2. Okay, and then from 3 forward, it's 0. So it's not difficult to write f of t in terms of elementary functions as follows. Okay, so first we look at this part. So it just is a ramp function. Okay, so this will be a nice representation until t equals 1. At t equals 1, we no longer grow with slope 1, but the slope becomes 0. Okay, so what we need is a negative slope of minus 1, and that should become active at t equals 1. So minus r t minus 1. And this correction, what's going to happen is, from t equals 1 to the future, we're going to stay constant at the value 1 for all future times. But there's another change that happens at t equals 2, and that changes this constant value drops 3 units, okay, and reaches minus 2, and it remains minus 2 for a while. Okay, so for that drop of 3 units, we need 3 steps, minus 3 steps, and that should become active at t equals 2. Therefore, we have t minus 2 for its argument. Okay, and then everything is fine for a while, but at t equals 3, another change happens, and that changes the value raises 2 units up. Okay, and remains constant there. So that means we have to lift everything up by 2 units, starting from t equals 3. So finally we have 2u t minus 3. And from that on, no change happens, therefore this is where we stop. Okay, and now let's try to figure out its time derivative, okay? F dot. Okay, this dot notation, we're going to use it frequently. It simply means that we're differentiating it with respect to its argument t. Okay, so what's f dot? Now f dot of t equals, now we're going to differentiate these and we're going to use the definition of derivative relationships between our elementary functions. The derivative of r is step, so we have u of t minus, here we have another u of t minus 1, and here we have minus 3. Derivative of step is impulse delta t minus 2, and finally plus 2 delta t minus 3. Okay, so that's what the derivative of f is. And if you want to sketch f dot of t, this is what you have. So it's u of t, okay, until t equals 1. And then from that you subtract this step. Therefore, because we have a minus 1 here, everything goes down 1 units and remain constant there. Okay. And then things will remain constant. 1, 1, 0. Of course, at t equals 2 and t equals 3, there's some impulsive thing going on. At t equals 2, we have an impulse with magnitude, well, not magnitude, but with the resulting integration giving minus 3. Therefore, at t equals 2, we have this, an arrow pointing down, minus 3, and at 3 we have another impulse. This time the sign is positive and the magnitude is 2. So that would be the graphical representation of this function f dot. Now we begin, let's end our discussion of elementary functions by an exercise. Okay. This is called the sifting property of the impulse function. And what you're asked to do in this exercise is to prove the following. Okay, minus t delta t dt. Now we said that the result of this integration is 1. Okay, you integrate the impulse function throughout an interval that contains in its interior the origin 0, and the result is 1. Now we're going to generalize that result by introducing a function that multiplies impulse within the integral. Now the integral, instead of impulse, it's some function times the impulse. Okay. Now assuming that that function is continuous, at least continuous at the point which makes the argument of impulse 0, in this case 0, the result of this integration is the value of this function at the point which makes the argument of impulse 0, in this case t equals 0. In other words, this integral equals f of 0 is what you're asked to show, provided that this function f is continuous. For continuous F. Okay. Well, of course, F doesn't have to be continuous everywhere. It only has to be continuous at t equals 0. And this can even further be generalized. It's not really a generalization, but we can write in general f of t delta t minus t0 for all practical purposes can be replaced by a constant times the impulse function, and that constant is the value of this function f at t equals t0. F of t0 delta t minus t0 for continuous f. Now, we're ready to talk about our dynamic components, namely, we will go through the properties of LTI capacitor and then LTI inductor. Let's begin with LTI capacitor. Now, we already talked about, in our very first lectures, we already talked about LTI capacitor and LTI inductor. We know its terminal equation, and we know that it, likewise, the inductor can store energy, and we derive what that stored energy is. So let's remember those ones. And to that knowledge, we will now put some further bricks. Okay. Now, LTI capacitor is described, okay, schematically by this picture. Okay. Plus minus V, its voltage, and we always respect passive sign convention. Therefore, the current has to be in this direction. And somewhere around this picture, you see a number or a letter C. Okay, and this constant represents the capacitance of the capacitor. And the capacitance of the capacitor is such that it relates the charge that's being stored in this device to voltage in this proportionality relation. Okay. So the voltage is proportional to charge or vice versa. And the proportionality constant is what we call capacitance of the capacitor. And then we have the definition of current, which is rate of change of charge, U over dt qt, and using these two equations, we can get rid of the charge q and relate or obtain a relation between current and voltage of the capacitor. Okay. So therefore we can write I of t equals c dvt dt, or I equals c times V dot. Okay. Or if you want voltage on the left hand side, then you have to introduce an integral to your equation. V of t equals initial voltage, which is related to initial charge stored at the capacitor, plus 1 over the capacitance, and then you integrate current. Okay. I tau E tau. Okay, so this is two equivalent representations of the terminal equation for an LTI capacitor. Okay, C is, we set capacitance measured in farads. Capital F. Now, the instantaneous power for LTI capacitor, for any two-terminal device, is the product of the current passing through it times the voltage that appears across its terminals. So P of T is V of T times I of T. And from this power, by integrating it, we obtained the energy that's stored in the capacitor. Okay? So let's also remember that. So energy accumulated in a capacitor during some time interval between T0 and T is, okay, so let's call it W for work, or energy. P0T is integral of the power, because power is derivative of energy or the work. V tau I tau d tau. And that can be written as from T0 to T V tau times, instead of current, we can replace it with capacitance times V dot. C dV tau d tau d tau. Okay. Then this can be written as V T0 to VT CV dV. Okay, now we're integrating capacitance times the voltage. Capacitance is constant, therefore this integral yields 1/2 C V squared. Okay? From VT0 to VT. And the answer is 1/2 C VT squared minus 1/2 C VT0 squared. Okay, so that difference is the energy accumulated during the interval from T0 to T. Of course, this difference could be negative. In that case, maybe in that case it means that that amount of energy, take the magnitude of this difference. If it's negative, well, if this difference is negative, that it means that that magnitude of that amount of energy has been given to the circuit that the capacitor is part of. Okay. And finally, let's remember what we mean by energy stored in a capacitor at time t, by definition, is Wt equals W minus infinity to T. And that, if you apply to the expression that we obtained, yields 1/2 C VT squared minus 1/2 C times square of the voltage at T equals minus infinity. And by definition, by convention, this is 0. Okay, by assumption, let's say. Therefore, energy stored in a capacitor at any given time is proportional to the square of the voltage at that particular time in the capacitor. Okay, so we have 1/2 C VT squared for the stored energy in a capacitor.